This is Math 1050 Final Exam Review, version A. Question number 1 from chapter 1, find the difference quotient. So what I'm going to do is actually focus on this little piece first, f of x plus h. Well, I'm going to do this separately. F of x plus h means that x plus h becomes an input in for x. So this is going to be 3 instead of times x squared is going to be times x plus h squared minus 1. And then x plus h squared is x plus h multiplied by x plus h. When multiplied together, we get x squared plus 2xh plus h squared, and then distribute the 3. So this is f of x plus h. So this is what replaces f of x plus h on the top left of this fraction. The top right is just going to be replaced with f of x. So now the difference quotient becomes f of x plus h, which is this, minus f of x, which is this. And remember, when you're subtracting an expression, subtract the entire expression in a parenthesis. If the negative sign were to distribute to both terms, this becomes a negative 3x squared, and this becomes a plus 1. So then the negative 3x squared here is going to cancel with positive 3x squared. This will become a plus 1, which will cancel with that negative 1. So then the remaining terms in the numerator, 6xh plus 3h squared, divided by h. Now, the terms in the numerator all have h in common, so we can factor out an h. And then that cancels with the h in the denominator. So the final answer is 6x plus 3h. For question 2, also from Unit 1, Chapter 1, find the inverse of the given functions. So for part A, let's start there. We're going to switch the place of x and y, or f of x. So for part A, I'm going to write x equals, because we're switching the place. And instead of f of x right now, just because it's easier to write, I'm just going to call it y. So y minus 1 plus 3. So now the task is to get y by itself. So got to subtract 3 from both sides. Then divide by 2 on both sides. Now square both sides. And finally subtract 1. Or rather add 1. Let's add 1 to both sides to get y by itself. And then the final step would be to use function notation. So there's part A. For part B, I'm going to start with x equals. We can switch the place of x and y. And then I'm going to multiply both sides by the denominator. So we'll multiply by y plus 3 over here and multiply by y plus 3 over there. Now we're going to get y by itself. So I'm going to divide the x over here. And then finally subtract 3. And use function notation. Question 3, using transformations So in this case, what you need to remember are the transformations that occur inside versus outside. These move it left or right. Remember, these move it up or down. This minus sign is going to flip. It's a vertical reflection. And then the 3 is a vertical stretch. That's the point here behind this question, is remembering what first of all, the parent function is just x squared. So this is a parabola. The vertex has been moved 1 unit to the right and up 2 units. So vertex is 1 comma 2. And the negative sign is going to make this an upside down parabola. And the 3 is going to stretch it vertically. So it's going to be a little thinner than a normal parabola. At this point, once you've identified the vertex, though, what I'd recommend is just finding 2 other points using a table of values. We already found 1 point, 1 comma 2, that's the vertex. So let's find 2 others. I would recommend you use x values that are close to the x value of the vertex. So I'm going to do 0. Plug 0 in for x. Subtract 1 is -1. -1 squared is 1. 1 times -3 is -3. -3 plus 2 is -1. And now we could use symmetry. So this point reflected over the vertex is going to be 2 comma -1. Question 4. This is from Unit 2. So finding the zeros of a polynomial was a very important topic in Unit 2. So for part A, listing the possible rational zeros, if you remember, the factors of 30, this is what we call the factors of P. So the factors of P are the factors of 30. So this is plus or minus 1, 2, 3, plus or minus 5, plus or minus 6, plus or minus 10, 15, and 30. And then the factors of Q are the factors of the leading coefficient, in this case, plus or minus 1. Now, the real list that we want for part A is P divided by Q. So since Q is just 1, all of these numbers divided by 1 are not going to change. So this list for P is also our list for P over Q because Q is just 1. So this is P divided by Q right here. So that's the answer to part A. Those are all the possible rational zeros to this polynomial. Now, if you remember, this is an x to the 4th. So it's a 4th degree polynomial, which means it can have 4 zeros. So there's way too many. This is why it's called a list of possible rational zeros. So for part B, the point is to now find which of these possibilities actually turn out to be zeros. And this is where you do synthetic division. So for part B, just going to start far left and do +1. And remember, for synthetic division, you use the coefficients of each of the terms. And if there is a missing term, including the number at the end, if any of these terms are missing, you have to put a 0 in its place for synthetic divisions. So 1, 3, 1, -7. These are just all of the coefficients. So looks like +1 does not work. -1 does not work. So found one that worked. X equals 2 is a 0. So now what we have is x plus 2, or rather x minus 2 is one of the factors. If x equals positive 2, then x minus 2 is a factor. Remember, these are the coefficients of a reduced degree polynomial, in this case a third degree. So it's x to the third plus 5x squared plus 11x plus 15. So we found one of the zeros. That's why x to the fourth is turned into x to the third. Now we need to continue doing synthetic division on this reduced polynomial. We've already ruled out positive 1, negative 1. 2 may be repeated 0, so if nothing else works, we could try 2 again, but I'm going to assume it's not a repeated 0 and move on to negative 2. Okay, so negative 2 didn't work. Try 3. Already tell that's not going to work. Okay, so x equals negative 3 is another of the zeros, so that means the factor is x plus 3. We already had a factor of x minus 2, and now we have a reduced polynomial factor of x squared plus 2x plus 5. So we need to find the remaining two zeros from this quadratic expression. This doesn't factor. X squared plus 2x plus 5 is irreducible. That means we have to find the zeros from that using the quadratic formula. So remember, the quadratic formula is the opposite of b plus or minus the square root of b squared minus 4 ac divided by 2a. So the opposite of b, as it relates to this quadratic expression, is negative 2. So then b squared would be 4 minus 4 times 1 times 5. 4 times 1 times 5 is 20. 4 subtract 20 is negative 16. Square root of negative 16 is 4i. And then both of these values are divisible by 2. So negative 2 divided by 2 is negative 1, and 4 divided by 2 is 2. So to reduce this, we get negative 1 plus or minus 2i. But then for part B, all of the zeros are x equals 2, x equals negative 3, and x equals negative 1 plus and minus 2i. So that's the answer to part B. And then for part C, we just need to list the polynomial in two linear and irreducible quadratic factors. So that's actually what we had here for part C. This is the factored polynomial with a combination of linear factors and then an irreducible quadratic factor. Question 5 from Unit 2. We need to create a polynomial now that has these given characteristics. So it's degree 3, so we know it's going to have 3 factors, which means it should have 3 zeros, but there's only 2 listed, x equals 1 and x equals 2 minus I. So what we assume then is that because there is a complex 0, x equals 2 minus I, then there's going to be a third factor, x equals 2 plus I. So now we have all 3 factors. So what we need to do then is create the polynomial first in factored form using the zeros. So if x equals 1, then x minus 1 is a factor. If x equals 2 minus I, and I move the 2 over by subtracting and add the I over, then the factor becomes x minus 2 plus I. And then here, if I subtract the 2 and I subtract the I, it's going to be x minus 2 minus I. Now we need to multiply this together because it says it has to have real coefficients, and these are imaginary numbers. So we're going to distribute each term here between these two parentheses. So x times x is x squared, x times negative 2x, and then x times negative I is negative ix. Now negative 2 times this x is negative 2x, and then negative 2 times negative 2 is positive 4, and then negative 2 times negative I is positive 2i. I times x is ix. I times negative 2 is negative 2i, and I times negative I is negative I squared. Now, a lot of terms, remember, will cancel. And then I squared is negative 1. So we have minus negative 1, which is plus 1, which adds to the 4, making 5. And then negative 2x and negative 2x combines to negative 4x. So that's x squared minus 4x plus 5 times x minus 1. So what we don't know is what is the leading coefficient. So when x multiplies x squared, we're going to get x cubed. That's going to guarantee it's a third degree, but it could be, 5x cubed, or is it 4x cubed or negative 10x cubed? We don't know what that leading coefficient is. So that's where this comes into play. If you plug a 0 in for all the x variables, then you should get negative 15. So negative 15 is going to replace this side of the equation. X or 0 is going to replace all the x's, allowing us to solve for a. So 0 minus 1 is negative 1. Then here's 0 minus 0 plus 5 is 5. So you know that the value of a is equal to 3. Okay, also from Unit 3, graphing rational functions. This was from Chapter 3. So show and label the vertical asymptotes for Part A. Vertical asymptotes are domain restrictions. In order to determine domain restrictions, we need to rewrite the function and factor the denominator. So the domain, which we're going to skip to Part D, is from negative infinity to negative 2. The reason we're taking out negative 2 is because x cannot equal negative 2. And then we're going to go from negative 2 to positive 3. And then 3 to infinity. So the exclusions, negative 2 and positive 3, those are the vertical asymptotes. And it says show and label, so we show them by that dotted line and then we label them like that. Now part B, show and label the horizontal asymptotes. The horizontal asymptotes that we learned about in section 3.1, 3.2 are the horizontal asymptote is determined by comparing the degree of the numerator to the degree in the denominator. This is degree 1. This is degree 2. So the determination there is because the numerator has a smaller degree, the horizontal asymptote is the line y equals 0. If the numerator has a smaller degree than the denominator, then the horizontal asymptote is y equals 0. If they're the same degree, if the numerator was degree 2 and the denominator was degree 2, then remember you would divide the leading coefficients to determine the horizontal asymptote. Okay, for part C, show and label the x and y-intercepts. So we'll do the x-intercepts first. For part C, to find the x-intercepts, we let y equal 0. And if you recall, for For this type of an equation, which is a fraction, because it has a numerator and a denominator, the only time a fraction is going to equal zero is when the numerator equals zero. So what we need to focus on is when does the numerator equal zero? And that's when x is equal to 1. So when you place a 0 in for y, we get a 1 for x. The x-intercept is the point 1 comma 0. Now the y-intercept we find by plugging the 0 in for all the x. So plugging a 0 in the numerator, we're going to get -1. I'm going to use this version of the denominator. With plug a 0 in for x, we get 0 minus 0 minus 6, which is -6. -1 divided by -6 is the point 0 comma 1/6, which is about right there. So the location of those 2 points gives us the idea that the middle part of that graph looks like that. So the discussion we had in section 3.2 and in 3.1 was the behavior of the ends here on opposite sides of a vertical asymptote. If the vertical asymptote comes from a factor that has even multiplicity, meaning how many times it appears. So if it appears twice, then the ends would be going in the same direction, in this case, both up. If the factor that produced this vertical asymptote has odd multiplicity, so x plus 2 is to the first power, that's odd multiplicity, then it means the end points are going in opposite directions. So if this is going up, this side's going down. Because of that, we can conclude that piece of the graph looks like that. Near the asymptotes have to be going in opposite directions because for this vertical asymptote, it was produced by x plus 2 to the first power, which is odd multiplicity. Using the same argument here, x plus 3, this vertical asymptote came from x minus, or x equals 3 came from x minus 3 to the first power. That's odd multiplicity. So it means near the asymptote, we're going to have opposites. So this is going down, which means this side has to be going up. So the other side of that vertical asymptote is going to look like that. Now we're into unit 3, exponentials and logarithms. For part A, we're solving an exponential. No, this is solving a logarithmic equation. So we're trying to get this natural log function all by itself so we can get rid of the natural log using a base e. But before we do that, we have to get rid of the plus 2 first, and then we have to divide by 3. So if we subtract 2, then divide by 3, now to get rid of a logarithm, you use a base. And it has to be a base matching the base of the logarithm. Natural log is base e, so it means we have to use a base e to cancel this. So those cancel out, and we have x minus 1 equal to e to the power of 7/3, and then add 1 to both sides. So the solution to the equation is x equals e to the 7/3 plus 1. Part B, remember that you must condense or combine logarithms into one single logarithm before you can solve equations. So if they're on the same side of the equation, which these are on the same side, and they have the same base, you have to combine them into one logarithm before you can solve. So since there's a plus sign, we're going to use the product rule, which means we combine these two expressions into a product or multiplication. So combining them into one single logarithm and then multiplying them together gives us x squared minus 3x. Now we can get rid of the logarithm by using a base 10. And now we have a quadratic equation to solve. Usually that involves getting one side equal to 0. In this case, we're going to factor. Now, Remember that it is possible to have what appear to be solutions that actually are not. -2 doesn't work because when you plug in -2 for this x or for this x, it comes out to be negative inside of a logarithm. Can't have negative values inside of a logarithm. So those are called extraneous solutions. X equals 5 is the only one that works. Okay, question 8. We're solving um, for how long will it take? How long will it take is a variable t for time. Now, there's two possible equations that it says we can use, but we have to use the correct one for this particular instance. If it's compounding monthly, then this is the compound interest formula for compounding at regular intervals. This is the continually or continuously compounding interest formula. So since it's compounding monthly, we're going to use this, which means n equals 12 because it compounds monthly. The um, P is the principal investment, that's $12,000, and it's going to double. So the future amount is 24,000, and the interest rate is 0.05. So what we're solving for at this point then is the variable t. I divide 12,000 over on both sides. So if we combine this, 1 plus 0.05 divided by 12, if we combine that and add that fraction to +1, it comes out to be 1.004. 166. Okay, so now we just have an exponential equation to solve. We're solving for the variable t, which is an exponent, so that means we're going to have to cancel a base. So we're going to use a logarithm on both sides, and the logarithm has to have the same base. So we're going to use a log of base 1.004166. It's going to cancel it there. And then divide by 12. The value of time is log log base 1.004166 of 2 divided by 12. So now this is something that would be typed into a calculator. We're going to approximate this. And I'm getting approximately 13.89 years. Also from Unit 3, graphing an exponential function. The difference between an exponential function and a logarithmic function, remember, an exponential function has a horizontal asymptote, whereas a logarithmic function has a vertical asymptote. So since this is an exponential function, we're going to find the horizontal asymptote first. Usually, remember, that's right along the x-axis at y equals 0, unless, like in this case, it's been moved down 1 unit. So the horizontal asymptote is the line y equals -1. All that's left is to graph 3 points, and I'm going to do a table of values with a few x values. So I'm going to choose -1, 0, and 1. If I plug in a -1 for x, -1 plus 1 is 0. 2 to the 0 power is 1. 1 subtract 1 is 0. Plug in a 0, 0 plus 1 is 1. 2 to the first power is 2. 2 minus 1 is 1. And then if I plug in a 1, 1 plus 1 is 2. 2 squared is 4. 4 subtract 1 is 3. Question 4. This is from Unit 4 now. Matrices and solving systems of equations. So in order to multiply two matrices together, the matrices of the number of columns from the first matrix has to match the number of rows from the second matrix. So matrix A is a 2 by 3, and matrix B is a 3 by 3. So since the inside numbers match, the multiplication is possible. So this first entry, we're going to go across the row, down the column. So 2 times 1, that's 2. 2 times 1 is another 2, and then 0 times 2. So 2 plus 2 times, or 2 plus 2 plus 0 is 4. This entry is going along the bottom row down the first column. So that makes negative 2 and 2 makes negative 4. Negative 2 and 1 makes negative 2. And then 1 and negative 2 makes negative 2. So we've got negative 4 plus negative 2 plus negative 2, which is negative 8. Here we've got 1 times 1, and then 2 times negative 1, and then 0 times 1. So this is 2, or this is 1 plus negative 2, which is negative 1, negative 1 plus 0. Negative 1, this entry here is bottom row middle column, so negative 2 times 1 is negative 2. Negative 2 times negative 1 is 2. And then 1 times 1 is 1. So we have negative 2 plus 2, which is 0. 0 plus 1 is 1. Here we have top row, third column. So 1 times 5 is 5. 2 times 4 is 8. And then 0 times 0. So 5 plus 8 is 13. And then finally, this entry is bottom row, third column. So that's negative 10. And that's negative 8. And that's 0. So negative 10 and negative 8 and 0 is negative 18. For part B, matrix B is a 3 by 3. Matrix A is a 2 by 3. So the middle numbers don't match. So part C is not possible, or part B is not possible. Excuse me, part C, 3A plus C. So 3 times A just means every entry in matrix A is multiplied by 3. And we're going to add that to matrix C. And remember, adding or subtracting matrices only works if the matrices are the exact same size. And these are both 2 by 3 matrices. We're just going to add the entries in the same spot in each matrix. So 3 plus 6, 9, 8, negative 2, negative 2, negative 6, and 0. Partial fractions were from section 6.7 in Unit 4. So um, first thing we need to do is look at the denominator in factored form, because remember the number of partial fractions is determined by the number of factors in the denominator. So factor it to x minus 5 and x plus 3. So since there's two factors in the denominator, we're going to have two partial fractions. And the next step is to multiply the entire equation by the lowest common denominator. When it multiplies all the way over there, the denominators is going to cancel with the lowest common denominator there. It's just going to leave us 3x plus 1. When it multiplies to the a, the x minus 5s are going to cancel. So then a multiplies with the x plus 3. And then when it multiplies, when the lowest common denominator multiplies to the b partial fraction, now the x plus 3s are going to cancel. So the x minus 5 multiplies b. So the method that was shown in class for this next part is just called choosing convenient values for x. So if I want a to disappear or if I want b to disappear, you have to choose x carefully. So if I want to solve for a first, I'm going to try to let x equal -3. So if -3 plus 3 is 0, means a is going to disappear. So let x equal -3. That's going to be -9 plus 1, which is -8. -3 plus 3 is 0, so a is gone, but -3 minus 5 is -8b. So b equals 1. Now, if we do this again, we're going to try to get b gone so that we can solve for a. So if I let x equal 5, +5, that's going to be a 0 here, allowing me to solve for a. So 3 times 5 is 15, plus 1 is 16. 5 plus 3 is 8. 8 times a is 8a, and then b is gone because 5 subtract 5 is 0. So a equals 2. So then the partial fractions, 2 replaces here, and negative or +1 replaces right there. So the two partial fractions are 2 over x minus 5 and 1 over x plus 3. Question 2. So we have an allowance here that's going to be 1 penny plus 2 pennies plus 4 plus 8 plus 16. And then day 30, we've got to figure out what was the total on day 30 and then what was the total amount received for the whole month, assuming the month is 30 days. So this is a geometric series. This is from Unit 3, Chapter 7. So this is a partial sum of a geometric series. So you'll be given a formula sheet on this final exam for formulas from Chapter 7. So the partial sum of a geometric series, and the reason I'm saying this is a geometric series, geometric is because we're multiplying by 2. So we're multiplying by the same value. So that means r is equal to 2. And the sum formula, the partial sum formula, so we've got first term, a sub 1, and then we have r to the, r is the common ratio, n is the number of terms being added together. So we have n equals 30, and we have a sub 1 is our first term 1. So we have all the values that we need to use this partial sum formula. We actually don't need the value all the way here at the end. The partial sum formula will take that into account. So we just need the first term, common ratio, and the number of terms being added together. So we have first term, so 1 multiplied by 1 minus 2 to the 30th power divided by 1 minus 2. So this is definitely a calculator problem. So this will give us the answer in terms of pennies. So this is 1,700 or 73,741,823 pennies. If we want that in terms of dollars, we're going to divide that by 100. $10,737,418.23. 1 month's allowance. Question 13 is from Unit 4, Cramer's Rule. This is from Chapter 6. Cramer's Rule involves determinants. And if there's 3 variables to solve for, then if we're going to solve for all 3, we would need 4 different determinants. But this one says only solve for z. So Cramer's Rule, if we're going to solve for z, means we need to find determinant d, and then we need to find determinant d sub z, and then z will be dividing d sub z by d. So the determinant d is just the determinant of the coefficients matrix. I'm going to do this determinant using the extended columns method. So you take these first 2 columns and write them over here. So that product, 1 times -1 times -1, that's +1. This product, 1 times -2 times 1, is -2. And this product, 1 times 2 times -2, -4. This product up that direction is -1. In this direction is +4. And then in this direction, it is -2. So those 3 numbers are going to add together. 1 plus -2 plus -4. And then these numbers are going to subtract. So subtract -1, subtract 4, and subtract -2. So 1 plus -2 is -1, plus -4 is -5, plus 1 minus 4 plus 2. We have -4 minus 4 is -8. -8 plus 2 is -6. So determinant d is -6. Determinant z, or d sub z, remember we take these values now, the 3 constants after the equal sign, it's going to replace the z column. So the z column is going to be replaced with 4, -1, and 1. And I'm just going to use the same method to extend the column. So this product is -1. This product there is also -1. And that product there is -16. This product is -4. That product is +2. And that product is also +2. So remember, these numbers add. So -1 plus -1 plus 16. These numbers subtract. So subtract -4, subtract 2, and subtract 2. So -1 plus -1 is -2 plus -16 is -18 plus 4 minus 2 minus 2. So -18 plus 4, -14. -14 minus 2 is -16. -16 minus 2 is -18. So finally, z is equal to d sub z divided by d, which is -18 divided by -6, which is 3. Question 14 is back from Unit 3, Chapter 7, when we were looking at arithmetic sequences and series. So first is, it was told that it's arithmetic, but we can verify that. We're adding 3 every single time. So we're adding a common difference. So for part A, The explicit formula for an arithmetic sequence is first term plus n minus 1 multiplied by the common difference. So here the common difference is d equals 3. A sub 1 is 11. So we plug in 11 for a sub 1 and 3 for d. We could distribute. So then for part B, to find the 49th term, we simply plug 49 in for n in the explicit formula. And for part C, the sum of the first 49 terms, so that's a partial sum of an arithmetic sequence. So the partial sum of an arithmetic sequence is half the number of terms that you're adding times the first term plus the last term. So the sum of the first 49 terms means we're adding 49 terms together, so n equals 49. The first term is 11, and then the 49th term we just found in part B is 155. So that's going to be 4067. Question 15, also from Unit 3, this is binomial expansion in section 7.3. We're not asked here to find the entire expansion of this binomial. We only want one specific term, and that term is the term that contains an a to the third. Now, if you recall, when we're expanding the binomial, it's going to be a combination of both of these terms raised to some power. So, and if we add the two powers, the power of a plus the power of b, it has to equal 6. So if the a is going to have a third, a to the third power, that means b also has to be raised to the third power. So the term we're looking for is going to be 3a raised to the third power times 2b also raised to the third power, and that's multiplied by a coefficient. That coefficient is found from Pascal's triangle, or one way we can find it is from Pascal's triangle. And because it's to the sixth power, we need 7 rows. 1, 2, 3, 4, 5, 6. One more row. And then we need the specific term that's going to contain a to the third. So the first term is a to the sixth. The second term is a to the fifth. This is a to the fourth. So this term right here, or this is the coefficient that's going to be for the a to the third and the b to the third term. So it's going to be 20. So this is 20. And then 3a to the third power is 27a cubed. And 2b to the third power is 8b cubed. And now we need to multiply 20 times 27 times 8. And that is 4,320 a to the third, b to the third.